thank you for joining the first lecture in a SIGGRAPH Now webinar series on machine learning and neural networks. My name is Christy Pran and I'm the SIGGRAPH 2020 Conference Chair. I'm thrilled to be here today to kick off the series for Rajesh, a fellow Disney colleague. Rajesh Sharma is a software engineer and he's contributed to projects at Walt Disney Animation Studios since 1998. His work in various roles has encompassed rendering, procedural effects, and animation software development, working closely with artists to develop the tools they need. Fun fact, Rajesh spent 2 months in 2019 embedded in Disney Research in Zurich to learn practical methods of applying machine learning models to denoising. So without further ado, I'd like to turn things over to Rajesh.
Thank you, Christy, for that introduction. And welcome everyone to this class. I hope wherever you are, you're safe and healthy. And we are going to go through a journey of learning what neural networks are and how to apply them. So it's going to be a course in a way where you can apply things. You might have taken a course on basics of machine learning, Andrew Ng's popular course on Coursera. But then where do you go from there? What do you do to apply these things to different scenarios? And this would help you get a step into how you can do that. So let's get started because we have about an hour to go, and then I want to cover a lot of different things. So this course will be basically an introduction to all kinds of people with all kinds of backgrounds. So you don't necessarily need to be a machine learning research person or an engineer or a practitioner at this point. And this course is going to help you get into that field if you want to. So we'll start today. We'll have a series of 9 lectures, and there'll be some homework, nothing too complicated or hard that will make you spend too much time, because I know nobody has enough time in the day, but enough to get you some experience on practicing these things, because that's the best way to learn, is to try things out and do different things. So let's begin in the beginning. Today we're going to introduce what machine learning is, what different kinds of neural networks are, and how do you solve a neural network, and then different kinds of neural networks, what they are and why they are the way they are. So that's today's agenda. And just to make sure that you have access to everything, there are links to today's slides and collab notebooks. If you log into your Google Drive, the moderators must have shared with you already this shared folder, and you can have access to the slides for today. If you are not able to see them clearly for some reason from this broadcast, you can bring them up, and then we will do some hands-on today. But in the future classes, we'll be doing a lot more hands-on, where I will be typing stuff so you can follow through. So, and then use the Ask a Question feature if you need to, if you have any doubts or something is not clear, if I'm going too fast or too slow. And then after the lecture, you can connect with me on Twitter, use this hashtag and find me on Twitter, and then we can chat and help each other out in learning this thing. So I want to look at this as a journey in which all of us are together. So if you find a fellow attendee struggling with something, just help them out, and we can communicate via all kinds of different means. But let's start with Twitter for now, and then we'll see where to go. All right. So let's look at the big picture. So you heard all these buzzwords like data science, business intelligence, analytics, big data, AI, neural networks. So what are all these things, and why do we hear so much about them? So if you forget about all these buzzwords, you can think of the entire thing as getting some data and then finding some insights from that data. So that's the entire purpose of the entire field, is to how do we make sense of this data? Can we infer something from it? Can we make decisions using this data? So all of that kind of works together to help you make sense of your data. So if you don't remember any of these things, just remember that it is data in, and then you are trying to make sense of that data using various means that are available to you. So AI and deep learning and machine learning, they're all part of this tool set that you can think of. So you don't want to use them as a big hammer on every problem, but look at them as tools that you can use. So in some cases, you would use AI. In other cases, you may not. So you may want to use some other method to make sense of your data. So we will learn through this course, like how and when to apply these techniques. So that's the big picture. So I'm not going to go through each of these boxes and tell you what they are, but you can understand that how these things are connected, essentially how to get all that data, process it, and learn from it, and gain insights and make decisions. So narrowing it down a little bit in the field of AI and machine learning, in the good old days of machine learning or AI, we would have these expert systems or knowledge bases where you would collect a lot of information about a subject and you would ask questions of it. You would have prologue-like logic that would be a little bit fuzzy, and you would kind of try to answer different questions from that knowledge base. And as the field has progressed, you have different tools become available. And the main reason these are more popular now is the availability of data. So there's so much data available now that we can make more sense of the data because of the availability, and the tool set has progressed as well. So availability of data, the progression of the tool set and research underlying that tool set, and then also the availability of cloud computing or lots of processing power. So all these three things together have made it possible for us to make sense of our data in a different way through deep learning, and we'll see how that is done. So that's like the onion chart that I got from this deep learning book. So this is, if you get one book on deep learning, this is the book to get. And it's also available freely on the website if you want to try it out. So what can we do with machine learning? So there are different kinds of things, right? So you want to look at what problem are you trying to solve. So you don't want to say that, oh, I got a machine learning algorithm, let me apply it to this thing. So you want to approach it from the problem side. What is the problem? And then what kinds of tools are available to me? So most of the machine learning things can be solved with either classification or some kind of regression or prediction. So, but there are special kinds of problems that you want to solve. Usually it's either of these questions on the left column, whether you're trying to answer yes or no. It's a binary decision. You're detecting something. You are detecting the presence or absence of something. And then the classification is one of the most common things that people do with machine learning, which is what kind of things is it? Is it a cat or a dog? Is it a bicycle or a car? So that classification of usually of images is a very popular thing to do, and it's very useful in many different ways. So, and then another application is, what is the size of this thing? So you can see in healthcare, you want to find out whether somebody has cancer or not, but not only that, but if there's a tumor, then what is the size of that tumor? So that kind of thing is usually done through segmentation. You must have heard of things like customer segmentation, where you take a customer set and see if they are going to buy at which price point, medium, low, or high. So same kind of thing you can do with your data. And you don't have to use machine learning for that kind of segmentation. You can do a simple clustering for that kind of segmentation. And then similarly, you want to predict a result, which is usually some kind of a value that you're getting out. So this is the classic regression problem, where you have a lot of data and then you want one value out. So you can apply this to many fields in different ways. And then finally, which is what is the next action that I should take? And that falls under the recommendation, where in retail, when you're buying something, you usually get a suggestion of, you may want to buy something similar that is this thing, or something that is usually paired with the item you're trying to buy. And you can see that in entertainment as well, where you watch a streaming channel and it would recommend to you different related things that you are accustomed to watching based on your profile and past behavior. So these are different kinds of things you can solve with machine learning, but you don't want to apply machine learning to every single problem. So what you don't want to use machine learning for is simple computation where you have known algorithms, you have simple rules that can be easily programmed. So if you have a closed form solution, there is no need to apply machine learning to that kind of problem. So when you do have a problem that is not easy to solve using simple rules, or the model is very complex, has too many factors, or if you have a very large number of inputs or factors that change your model. So in those cases, you do want to try and apply machine learning. So that's like the basic introduction, and I hope everybody is following along. If not, ask a question in your panel. Moderator would tell me what kinds of problems you're having understanding this. Otherwise, we will go ahead. So how do we do this? So it can seem pretty overwhelming. You got a ton of data, and then you want to predict something, but you don't know where to begin. So I put together this simple list of things that you can follow. And it's a linear list, but usually you are going to go iterate among different things. So first thing what you want to do is you want to say what is the answer you want to predict and what is being observed. So you don't start with the machine learning algorithm itself, but you start with the problem. You frame it in a way as what does my data show and what is that I'm trying to predict. And then you collect your data. So you collect your data, you clean it, you prepare it. Your data might come from different sources. You may want to bring it in a way where it is all clean and remove data that is suspect. You want to transfer some of the data in a different format because you're collecting it via, say, surveys, or you're collecting it through some IoT devices, or any other form that you can get your hands onto your data. So once you have your data, you analyze the data. So does that data make sense? You can visualize it in different ways. Are there any obvious correlations among your data? And that way you can prepare your data, you can align it with your final objective. And once you have that, you can transform your data, because some of the data may be in different units. Others may have ranges that are so varied that it is hard to combine different kinds of data into one data set. So you want to process and transform your data a little bit to be able to predict it better. And then you build the model. So model, you choose a model that is available, or you can build your own, and you design this learning algorithm that can solve your problem. And once you have that, you can start training. So you train your network, you feed the data to the model, and then you see if it is performing well. Is your model learning from the training data? Is it able to predict properly or not? And then finally, once you're happy, you start the prediction. You can use that model to generate predictions for new values that the network has not seen before. And that's the whole purpose. And once you're happy with it, you take that model and you deploy it. And you can deploy it in different ways. You can deploy it via a cloud or by some services that people can use, or you can just incorporate that into your software somehow. So that's the end goal, is to deploy this trained model with weights, and we'll learn what the weights are and how to solve for them. So that's the process, and it's not going to be linear like this. You're going to get stuck in a place where you're going to move around and you're going to try the model is not correct, you're going to replace the model, your training is not progressing, you're going to adjust some parameters for the training. So all those things are iterative, just like programming, where you don't follow a linear process, but you go through some iteration of different pieces of the process. So as in programming, you know that most of the time, for even experienced programmers, you would spend in fixing bugs and trying out different things. And same with the machine learning as well. You would spend a lot of time doing data analysis and feature processing and data collection. And model building is actually the easier part. So model building, because of the research that is going on in this field, there are so many different models to choose from. They're pre-built and you can use them. So most of your time is actually going to be spent in data analysis and feature processing and training and prediction, and those kinds of things. So so this is basically a process that I follow, and then I would recommend that in the beginning you kind of try to follow this and then see where it takes you, and you can modify it to your needs if need be. So most of the time when you learn machine learning, usually they teach you about different models, things like back propagation and matrix multiplication and all those things. So we're going to approach it from a very simple, intuitive way, because that's how I learn and that's how I teach. So what I want to do is help you build a mental model of like how these things work, what they are. So we're going to start with a very simple problem of this kind of data you might have seen before. So you assume that you have collected this data from somewhere, and it's a correlation of some kind of number of bedrooms for a home and the price of a home. So now you're trying to figure out like how can I predict, given the number of bedrooms in a home, what the price is going to be. So you have all this data available to you. You look at it, you analyze it, and then if you were doing this as a traditional program, you would try to kind of put a line through this data and say, or a curve, and say, okay, this looks like y equals something or the other, and that's the equation of my thing, and that's you're done. So that's a simple program. You have formed a model, which is a simple straight line that kind of fits through this data. It's not going to fit all the data because the data is not in a straight line, but you can see that it kind of falls along this diagonalish line here. So then you can start predicting. So what you do in that case is you have this straight line that is the predictor for your number of bedrooms. Given the number of bedrooms, you can predict the home price. So you can model this. And then someone comes along and says, hey, what about these things over here? Looks like we are not covering this data that is just below the line. Looks like there is a cluster of them. What do we do about them? So if you were writing a traditional program, you would try to put in a little bit of an if statement there and see if something is less than 5, but something is that, and you would try to program it in so that you cover this data as well. So your straight line now becomes like when you introduce an if, you introduce some kind of non-linearity into it, and then you can cover this area as well. But then what does this area represent? So you don't know that. So what you do is you go to somebody who's an expert in selling homes and say, hey, what about this data? What's wrong with this? Why is it not fitting in a straight line? And they say, oh, that's because of the zip code. Maybe these set of homes belong to an area that is say near a power plant, or maybe it's on an earthquake fault. So we don't know that. Why are these home prices depressed despite the bedrooms increasing? So you consult an expert. So ultimately what will happen is you'll consult a lot of experts and you'll make up these rules. So in that case, you would have then gone from simple programming to some kind of a knowledge-based system. So then lots of different features can affect home prices, not just the bedrooms. So you can keep adding different if statements, different rules, but then it becomes pretty cumbersome over time. So what you can then do is try to use a data-based approach where you say, I'm going to use not just the number of bedrooms, but I'm going to use some other factors and see what other things can influence home prices. And we'll do that in next class, but let's follow through with a straight line approximation and see where it gets us and what limitations it has. So once we have that, so now the question is, like, we came up with this straight line and it was pretty ad hoc, and I just drew the straight line, and there is a mathematical way to come up with the best possible straight line that fits your data in a linear way. So the way to do it is you take all these data points that are available to you, and you drop them on this arbitrary line that you choose. So then you have these green lines that are the distances from your predicted line. So what you do is then you start turning this straight line until these distances become as small as possible. So once you have that, then you have found your best fit line. So that's easy to say, but then how do we do it mathematically? So one common way to do that is something called the sum of least squares. So the way to do it is you take all these points and you find these distances. So these vertical distances, we're going to call them error, because they are the error in your prediction. So your prediction line, remember, is the blue line with the y hat I, and your actual points are yi. So your prediction error is basically the difference between the two. So now we can start to formulate some mathematical things around it. We say that our prediction line is y hat equals ax plus b, where this is an equation of a straight line. A is the slope and b is the intercept. So b is the y-intercept. If you extend this blue line a little bit below, in this particular case, it's probably something around 2. And then you have the error. So it's not enough to minimize one of these. You have to minimize all the points simultaneously. So what you want to do is minimize the sum of all these errors. And because these errors can be negative or positive, depending upon which side of the line you are, we just square it. So squaring it basically makes everything positive. And it has other nice results as well. But for now, we are squaring it because it makes everything positive. And so the total error, or the total squared error, would then be the sum of all these differences. So all these green lines, that distance would be the sum total squared error. So then all you have to do is minimize this. So expanding this for y hat I, you get this kind of equation, and you minimize it. So how do you minimize it? We'll go over that now. And then A, B basically are parameters. And these are also called weights, and you'll learn why. So essentially, you're trying to find A and B that are going to minimize this total least square thing. So let me pause for a second, because this is a lot of math I just said. So it's basic math. It should be accessible to you. And if there's any issues, let me know. So I'm going to take a little bit of a pause and see if there are any questions, and see if I can answer. So I'm going to type answers for now. I'm going to do live answers for now. The easy ones are, what do you mean by feature in feature processing? So feature processing are basically different kinds of your input data. So in our particular case, the number of bedrooms is a feature. So there might be something else like, say, the zip code, or what else can be a feature in this case. You can have the square footage as one of the parameters. So that's that. And so somebody else has a question, why bedroom number can be a non-integer? So that's a great question, because the bedroom can be, ideally you would want bedroom to be all integers, and it doesn't make sense for it to be, but the way the math works, so you can have non-integer values, and that's totally fine. So that's a predictive thing. And then we'll cover on like why or how these data we arrive at, and when we clean them and when we transform them, they may change values, and that's okay. So in the straight line equation, somebody has a question. I'm not sure where A and B came from. So A and B are basically the classic equation of a straight line, which says that any y equals slope times the x value plus some intercept. So that's a linear equation. So x and y have a linear relationship. When you draw something like things, when they go through the origin, the intercept is 0. So slope is just whatever y over x is. So that's where A and B come from. In our case, we are choosing A as the slope and B as the intercept. Okay, so I'm going to pause again, and let's go back to the class. So I might answer some more questions later on. So hopefully that is good. So next is, once we have this, so we focus on this particular equation where we are trying to minimize this. So in math, when you have something you want to minimize, you differentiate. So you do partially differentiate with respect to A, and then with respect to B, and then set that to 0, and then you solve for that, and then when you get that answer, you plug it back in. So that's a good closed form way of solving it. But when you have lots of data, lots of weights to compute sometimes, an easier numerical method is to do something called a gradient descent. So in gradient descent, so remember we are differentiating, so these things are called gradients. When you have a shape, so if you look at this particular equation, it's got a square in it, so it becomes a surface. So it's a surface, something like this. So you start somewhere arbitrary, and then you take a step forward. And when you take a step forward, you try to figure out whether you're going downhill or uphill. So if your idea is to go downhill because you're trying to minimize the gradient or set it to 0. So as you keep going downhill, take small steps at a time, you ultimately try to reach the minima, which is the lowest point possible. So there can be multiple minimas. If the surface is not nicely shaped like this, there may be hills and valleys and saddles along the surface. So you may want to take small steps at a time, try to figure out where to go next. So this method, like because you're descending and you're computing gradients, is called gradient descent. And it's one of the most common ways we solve for weights. So ultimately, you're going to find the correct A and B, or the A and B that minimize the sum of the least squares, and that would be your answer. So that's how you solve for weights. So once you have that, so if you look at this equation, and now we want to turn our attention to like how can we make a network out of this. So linear equation is all well and good, but then what does it mean if to solve this using a neural network? So we can take this and rejigger it to look something like this. So if you think of 2 inputs and 2 weights, and you combine them in some linear way, where you multiply each of these weights by the input and sum them all up, and that is essentially the equation of a line. So in this case, where if you substitute for different values, you will see that these are basically equivalent. So a simple network like this is representing via linear algebra, basically, as a sum of weights, where your weights are the slope and the intercept. And you can also reformulate this as a form of a matrix. So there are 2 matrices here. One is this horizontal matrix of input parameters and this vertical matrix of weights. And if you know matrix multiplication rules, it's basically this multiplies with W11 and I2 multiplies with W12, and then you sum them up to get the results. So in a simple case with 2 inputs and 2 weights, you can formulate this as a matrix or an equation of a line, or you can think of it as a linear function of weighted multiplied with input parameters and then all summed up. So everybody clear on this? Because this is an important kind of transition from algebra to linear algebra to matrices. So because once we have the matrices, we can use the computing power, the awesome libraries that are available to do all kinds of multiplication. So if you had one input set of I1 and I2, you can do this multiplication. If you had another set of data points, I3 and I4, you can put them below it without having to change anything, and you can put them all in this big vertical matrix and multiply them simultaneously at the same time. So that gives you a really good computing method to solve these things. So it's a key step in kind of solving for, because everything ultimately boils down into matrix multiplications. So I hope everything is clear on this thing. So this is a crucial result, and then we'll be expanding on that and building more complex structures based on that. So next up, you can see that we have these data points and ours were in a straight line. But what if your data was like this? And if you try to fit a straight line, it's not going to cover most of the points. If you try to take some kind of non-linearity into account, where you try to fit a polynomial of degree 2, and you see that you have a much better fit. And you can go overboard, and you can try a polynomial of a very high degree to fit as many points as you can. And in practice, you don't want to do that. Although this is a great fit for your data, it loses the predictive power. So this is also called overfitting, and you want to avoid that. And in the same vein, you want to avoid this, which is called underfitting. So you want to have some sweet spot where whatever set of functions you come up with, they kind of cover the data most of the way and leave some room for prediction, because you don't want to memorize the existing data. The whole reason you're doing this is to be able to predict for new data that you haven't seen before. So, so keep that in mind. So this is underfitting, overfitting, and this is just the right fit. So we've done the linear equation. So this particular network solved for linear equation, and that was fine. How do we get into the curve part of it? How do we approximate functions that are curved? Can we just square things? So that could be like tedious, because you don't know beforehand what kind of shape your data might have. So you may not want to ad hoc approximate with a high polynomial function. So you want to naturally discover the shape of the function that approximates your data. So the most common way to do that is just tack on another function after you have summed up your weights. So, and this function A is called the activation function. And the most popular activation functions today in practice are the sigmoid and the rectified linear unit, or ReLU. So these are the equations that govern these functions, and these are the shapes of these functions. So as you can see, this particular function, the sigmoid, it kind of forces you into a somewhat binary decisions. It takes the values and then pushes them towards either 1 or 0. And and then because of the shape of it and the exponential here, it introduces non-linearity. So all you have to do is you follow the same thing. You take the inputs, multiply by them weights, and then sum them up. and then apply an activation function on top of that. And that is all you have to do to introduce nonlinearity. So what we have done now is modeled a simple neural network. This is modeled after, we call it a neural network because it looks kind of like the neuron setup in the brain. So it's not exactly the same, but it's pretty similar. So if you look at the picture of a neuron or the diagram of it, you can tell that this dendrites, they are the inputs, or they're the nodes that take in the inputs, and this cell body is where you do the summation, and the activation happens in the axon, and then you get the outputs, and you can imagine these outputs are connected to dendrites of other neurons as well. So you can have multiple connection of neurons going on at the same time. So just remember that it's a loosely formed after a real neuron. So that's why it's sometimes called artificial neuron, and the neural networks are also called artificial neural networks as ANN sometimes. So it's just a model based on an actual neuron. So let's pause here because we covered a lot of things, and I just want to answer some more questions. So somebody had a question that whether a weight represents a feature. So no, the weight is not the feature. So weight is something that we are trying to find. So the feature is multiplied by the weight, and that gives you the output equation, right? So so the features are different from the weight. So somebody else has a question about why don't we use the closed form algorithm? So yes, so for linear regression, there is a closed form solution, and we can program it, and it works fine. So this is just a building block for you to get to the next step. So once we get away from linear part of the linear regression, then things get more complicated. Once you have multiple values, instead of just the number of bedrooms, if you had 5 or 7 features, then things become more complicated, and the closed form solution is harder to get. So the nonlinearity and the number of features, so that is the reason why we try to use machine learning for this, because the closed form solutions doesn't apply. All right, so somebody had a question, why is overfitting a problem? Will it predict wrongly? So yes, the answer is that it will learn the data, and the prediction value from for new data is going to be like, it will try to give you some data back that it already knows the answer to. So yes. All right, so there are a lot more questions, and which I hope we'll collect them and I'll answer them offline, but let's move ahead. So now we have added nonlinearity, so we can add complexity as well. So we can add complexity by adding more layer into our network. So this is the same diagram as this, except now we have added more input nodes here, and then we have an extra output in this particular diagram. So what this does is basically adds a little bit more complexity to your network, but the overall idea is the same. So each node in these things are called layers, and the vertical circles, they are layers, and anything that is not an input and an output is called a hidden layer. And so you can take a node and it's connected to every other node in the next layer. So basically, if you have 4 here and 1 here, then each one of them is connected to the next one. So same thing for this node, and then in the next layer, you follow the same process. And essentially, this is called a fully connected network because everything is connected to everything else in the next layer. And what we do here is exactly the same that we did here. In a simpler network, you take the inputs, you would have some weights, and then you would multiply those weights, you would sum them up, and then you would apply an activation function, and whatever output you get, you pass it on to the next layer. So it's the same mathematical process, except you would have multiple equations here, all of them taking this weight and multiplying it by the input, and then summing it all the small little equations here, and then applying the activation function at each node, and then moving forward. So in essence, basically, it's very simple, similar network to this, except we have added another hidden layer here. So what I want to emphasize now is this simple network is capable of solving any function. So even at this state where you have only one hidden layer, you can solve any function. So that's a pretty strong statement. And the reason why it works, we'll cover it briefly. So there's something called a universal approximation theorem. And it says that a single hidden layer containing a finite number of neurons can approximate any continuous function on the subset of real numbers. So that is pretty shocking because you have a very simple network here. With some nonlinear activation function, you can solve for any equation, because you can think of all functions being composed of some linear combination of other functions. So there's a caveat to that. We need a lot of data. So we need a lot of data from a nice random distribution to be able to do that. And we need a lot of computing power to be able to do that. But in theory, you could use this network and solve for pretty much everything. So this should basically make you go build this network and solve for any problem you have, provided you have a lot of computing resources, a lot of memory, and a lot of data available to you. So everything else you will learn in machine learning is about optimizing that process. Is all different kinds of networks, all different kinds of ways to solve for them. They are a result of trying to optimize this so that we can do what we want in the finite amount of time we have, in the finite amount of resources we have, and in the finite amount of data that we have available. So keep that in mind, that you can always go back to this simple function if you have a ton of data, a ton of compute power, but everything else you will learn in machine learning is about optimizing this process. So with the universal approximation theorem, this is kind of a gift, but it comes with a caveat where you can only solve for a class of problems at a time. You cannot create a general solution for everything. So each kind of network you do is going to solve for a specific set of problems, because on average, if you try to solve for a very general thing, it is going to degrade because it basically tends to be the average. So that's two things to keep in mind, that you can solve for anything, but you cannot solve for everything. Okay, so that was the basic theory for it. So how do we solve it then? So what we're going to do is, so remember, we are trying to find these weights. Once you have the weights, then you can take any new input, multiply it by weights, because now the weights are known, and you are going to sum them up, apply an activation function, and that is your prediction. So this is this simple step. You will repeat it again and again, and you can go through all these nodes and predict your output. But then how do we solve for weights in the first place? So you're going to start with setting the weights randomly initially, and you're going to make a forward pass computing the values for the output. And because of the given data, you will have a real result to compare with. And if the results that you have computed is different from the real result, then you'll find your loss. And once you have that loss, using that loss and by changing the weights by a small amount. Remember how we talked about gradient descent, that you take a small step and you walk down the gradient hill, basically, trying to find the next step that will minimize the gradient. And you take that small change in the weights, and then you recompute the weights based on that. And that is essentially called back propagation. And the way it works, it's mathematical in nature. It's based on partial derivatives and numerical stuff. And I'm not going to cover that in detail because most other classes kind of make you spend a lot of time trying to compute gradient descent. It's available in most toolkits, but if you're interested, you can go back. So all we are doing is changing the weights slightly and then updating all the weights in all the nodes. And we do this repeatedly until we minimize the error, or sometimes it's called the cost. So this process is common. It's done for every kind of neural network. And there are some names for these things that are used in literature and in textbooks and in the software. So I'm just going to go over that. So most of the common names are underlined here. So input data is also known as features, like each of the columns in the data, like the number of bedrooms or the zip code or the square footage. Those are all features, sometimes also known as X or attributes. And the output that you are trying to predict, if it's a classification, they are known as labels, also Y corresponding to the X, and also sometimes known as the ground truth. So ultimately, all you're doing is trying to approximate a function that, given all the input, what is the Y. The network itself is sometimes called the model that you build. And the loss function is the difference between, like in the least squares, the square, the sum of squares was the loss function. So that is the thing that you're trying to minimize usually, also known as metric sometimes, or the cost function. And activation function we already covered. It's like the sigmoid or the rectified linear unit. Its main purpose is to add nonlinearity. And then when you are updating the weights and you're doing back propagation, feeding in all the data, that part is called training, sometimes known as fit. In TensorFlow, the process is called fitting. It's an optimization step in a big loop that is trying to minimize this loss function. And then there is also something called evaluate, where you are trying to figure out whether the results make sense. Is your error actually decreasing? Is your performance good? Are your answers correct or not? And then finally, the prediction part is also called inference sometimes. And that is what you do on new data that the network has not seen before. So that is the terminology that most people use. It's in textbooks and other places that you will find. So don't get confused, just come back and look at this summary and see what they mean. And once you get used to it, you can move back and forth between different labels that people give to different things, and it's totally fine. So nothing is standardized. They're all kind of, you have to keep in mind what they mean when they say different things. When they say fit or training, it's actually the same thing. So let's take another pause. So looks like some people have problem with the link and they found it. So there's a folder that has been shared with all of you, and you will find the link to the Jupyter notebook or the Colab notebook, and also the slide deck in PDF form. And if you're not able to still, please put the question in chat and we'll find it out. So okay, let's see. So somebody's asked, can a single layer neural network even approximate a periodic function? So the answer is yes. So it does, and it can. And then you can actually try it out, and we'll go, I think after you go through the second class, you should be able to try it out and prove it to yourself. Okay, so looks like most people are able to access the spreadsheet. So in particular, the Colab notebook, you have to enable the Colab app to open it. First time when you open it, if you have never used Colab before, you will get this issue where you're not able to open it, and that's fine. So let's go through some of the applications. If you are all coming from a computer graphics background or interest through SIGGRAPH, we can apply machine learning to a lot of the problems that we face in computer graphics. One is basically scheduling for optimization, which is like how much memory to allocate, how many processors to allocate to something. If you have a render farm or a queue of some kind, you can learn from the past behavior of what you do, and then you can allocate things better. So this is a pretty common application of machine learning. You can do character AI for games. You can have behavior that is, you can program and train with machine learning. You can do style transfer between different image styles. That's pretty common, and most of you probably have seen it, where you take a Monet style and then you take a picture taken somewhere else, and then you transfer the Monet style onto the picture. You can do a super slow motion using machine learning. You can also, it's a form of a frame interpolation, and we'll go over it, how to do that. You can up-res images, you can denoise images, and you can do something with text. You can learn about story sentiment, how people might react to the story that you're trying to tell through your game or your film or your show. And then there's a class of applications where you can do something called rough to fine, where you have rough result and fine results, and then you can train them in pairs, as where fine is the answer and rough is the input training set, and then you can learn to create a fine result from a rough result. So that's a pretty common application throughout computer graphics in general. You can do body tracking, you can do facial tracking, you can do hand tracking, learn from that. You can design a gestural language based on tracking things. So that is also pretty common and growing application of machine learning into body tracking. You can create new images. You must have heard of deepfakes, but there's other applications of that using generative adversarial networks. So new image generation is a pretty common application as well. So we are running out of time a bit, but that's okay because we can just continue on wherever we left in the first class. But I want to get some hands-on stuff done, so you get used to just using the Colab notebook, and it'll give you some time between now and Wednesday to try things out. So we are going to use Colab. It's a Jupyter-derived IDE, Python-based. We can use Python 3.0 or 3.x and TensorFlow 2x wherever possible, and NumPy for all kinds of math stuff, Pandas for data analysis, Matplotlib for plotting. So again, don't be intimidated by the number of packages. So one thing you will learn with machine learning is that you take in whatever tools are available. Get your work done. Do not try to get sidetracked by like learning everything about NumPy or everything about Matplotlib. Just use it for what it is good for, and use it for solving your problem. Remember, you're focusing on machine learning, and you can go and spend enormous amounts of time trying to find intricacies of Matplotlib or NumPy, but you don't have to do that. So you have to train yourself to kind of just get the package, use it for what it's good at, and then apply it to what I'm doing currently. And that will help you kind of not just in this class, but everywhere else as well. Because we have a tendency to get sidetracked and go into this deep hole of, have you ever opened tabs after tabs after tabs, following links? So it's the same kind of issue where you can kind of try to focus on the problem at hand and then use whatever tools necessary to get things done. So having said that, let's open up our housing data file. So if you can follow along with me, this is a simple file. It's a Python. If people who have used Python before, this is going to look very familiar. All it has is the imports of some packages we're going to use, and we're going to alias them so we don't have to type as much. And so these are the packages. So in Colab, if you follow along, this arrow is what executes the code snippet, and you can put your code in small code snippets so you can execute them by parts. So this gets executed. Everything got imported that we needed, and we may not use all of it, but it's totally fine. So what we're doing here is we are reading a file, and we're reading a file from somewhere from Google Cloud, and it's called California Housing Training .csv, and we read it. So pandas is what we're going to use to read it. And if you hover over here, it will tell you what these functions do. You can read about them, but all it's doing is reading a file and using the comma as the separator. So it reads it all up here. Let's execute that. And there are different things about pandas. You can find out more about your data. So shape is like what is the dimension of your data. It is basically read as a matrix. So 17,000 rows and 9 columns. So that's information. And then we print the head function prints 5 or gets the first five elements of your frame. And you can see that these are the first 5 values. So these numbers are not part of the data, and these are the labels, and this is the actual data. So you get 5 sets of data. It has these elides here, which mean there is more columns. As we know, there are 9 columns here, so only 4 are shown here. So what we can do is we can transpose this. We can transpose this so we can see all the names of all the columns. So these are the names of the columns, and these are our 5 data points. So you can see it has some information about location of a home, longitude, latitude, median age of the home, total bedrooms, population, household. So you can see there's something called population. What does that mean? And households, what does that mean? So it's not data per home. This is a census data from a block. So there are multiple homes in this area. So then the median age is per home, but the population is the population of the block, and the households is the number of homes in that block. So that's just to keep that in mind, that this is not data per house, but data per block. So you can also do something called describe, which gives you small little statistics about the data, which is the count, number of data points, the mean of the longitude, the different percentiles, and the maximum and the minimum. So you can print that in a different way. So if I were to not do the transpose, I can do that. So moving on quickly, we can print the latitude and the longitude only, like 2 columns. And we can plot longitude versus latitude with the size as the total bedroom and some transparency. So this is latitude versus longitude, and you can see that it is the map of California, and which is what we expect it to be, because all these homes are in California. This is California data. And so this is awesome, because now you get some insights from your data. If you have ever been to California, looked at California map, so you can see that most of the homes are here. This is probably LA, the Bay Area, San Bernardino. This all empty area is probably the desert, Sierra Nevadas. So you can get some insight from your data just by plotting it simply. So let's plot everything against everything. So basically we got to take 1, 2, 3, 4, 5 parameters. I'm going to plot them against each other. So you're going to get 25 graphs, and they basically plot each of those parameters against the other. So you're going to get 25 graphs, and in the diagonal, because it's the same parameter, the Seaborn toolkit, it basically gives you the distribution. So distribution should actually look like a normal distribution. And if you look at the latitude versus longitude, it doesn't look like the map of California anymore. So what happened here? So we took 1,000 data points, but we took them from the top. So it's kind of biased in a way, because it's not taking data that is representative. So this is something that you want to be mindful of in all machine learning. So you always want to get random enough data so that it is representing the entire data set. So whenever you draw a sample, you want it to be not biased. So you don't want to just take the top 100,000 items, because if you look at the latitude versus longitude map, you want it to still look like California, but just a little bit sparse. So what we're going to do is we're going to sample instead. So this is going to do a random sampling of 1,000 points from your data set. Remember, we have 17,000 data points. So this is going to be of a more representative of your data set. So now if you look at latitude versus longitude, it still looks like a map of California, which is pretty good, just a little bit sparse. And you see the things are a little bit more normally distributed here as well. So that is also good. So that's all the hands-on we have time to do today, but you can go home and try it out. You're already home probably. So try it out, try different things with this data. And next time, so I'm going to skip a few slides because we didn't get to cover them today. We'll cover them next time. So next class, we will cover TensorFlow. We will import that package and start using it. We will do regression. We will do classification. So in the meantime, just play with the data you have in the Colab notebook. Try some other plots, see different relationships. If you can see any obvious correlationship between different parameters, what do they mean? Does it mean that number of bedrooms has a correlation with the home price? What about the population? What about the zip code? Coastal areas, can you plot just the coastal areas and see what happens? So, and then in the meantime, if you have any questions, you can reach out to me on Twitter. Use this hashtag, talk to me, and if you have any questions at all, and let me know. So let's stop here, and I will take a few more questions, maybe if you have time to stick around. Right, so somebody was saying the housing file has a syntax error in the last line. So that's on purpose. So I wanted you to type this thing. So you put a sample thing. So it's very similar. So I can kill this. So the last line is very similar to the previous line, where you're actually now taking samples from the data instead of just taking the first 1,000 samples. All right. So I think what the moderators might be able to do is take all these questions and then maybe send it to me. And then I will answer them on Twitter, and you can follow along. Is that good? All right.